Okay, let's talk about scaling, translation, and elasticity in this lecture. We'll start with scaling. What is scaling? Well, scaling means that you are changing the units in which your x or y variables are measured. So changing units means you are dividing the x or y variable by some number, or you are multiplying them. So going from centimeters to millimeters by multiplying by 10 is you are changing the unit or scaling the units. That's what scaling is. It's a simple procedure, but we are not interested in scaling for its own sake. We are interested in what it means for our regression coefficients. So if you had a model where you were estimating yield as a function of rainfall, rainfall is measured in inches. And you get this relationship which says if you look at yield, the model that describes yield is that yield equals 1,500 kilograms plus 500 times the amount of rainfall measured in inches. Now, if I go into measuring rainfall using millimeters, what happens? What do I get for intercept? What do I get for slope? That's what we want to know. Well, most important lesson is that scaling cannot change the nature of the relationship. It cannot change the story. The original story will stay the same, but the coefficients will change to maintain that the story is not changed. And that's the most important lesson about scaling. So if you had an original regression where y was regressed on x1, we are writing x1 here because you might have different variables x1, x2, so you can just think of x for now because we don't have anything else. So if you scale the x variable by dividing it by a number s, okay, s could be 10, could be 100, could be 0.1, it could be 0.01, it doesn't matter. If you scale it by s, then what has to happen is your coefficient will have to adjust to maintain that the story is the same, so that a change in your new variable is not going to lead to a different story. It has to lead to the same story. So the coefficient value will change by what you see here, which is it will be multiplied by s. And that's how it works. Okay, so if we look at this, now yield was described by this equation before, but now we want to change inches to millimeters. Well, going from inches to millimeters is you multiply by 254. Well, that means I need to divide by 1 over 254. This is just the same thing. So what I am doing is, well, I am going from my old variable in inches to my new one, by multiplying by 254. So the s is 1 over 254. But then my slope term has to be, as we said before, the old one times s, except that s here is 1 over 254. Okay, so if I do that, that coefficient is going to become smaller. So what do I get? Well, I get this equation. Or if I round up the 1.97, it becomes what you see here. So this equation and that one are the same, except for the unit change. They are the same thing. So the old one was saying, well, an inch will give you an extra 500 kilograms. So if you get an extra inch of rainfall, you get 500 kilograms of yield. Well, this one is saying if you get a millimeter in extra rainfall, you will get 2 extra kilograms. They are the same because an inch is 254 millimeters. Roughly, if you think 250, so an inch was giving you 500, so a millimeter is going to give you only 2. So that's how it works. Very intuitive, very simple, and that's what scaling is for the x variable. Now, you can, of course, scale the y variable. So if you scale your y variable, you change your units on the y. For example, going from kilograms to tons, well, that means you divide your y, which was in kilograms, by 1,000 to have it expressed in tons. Then what's going to happen is, well, if I divide one side of the equation by 1,000, I have to divide the other one by the same number to maintain the relationship. So what I'm going to get is a different intercept, a different slope. And basically what I'm going to have is something like 1.5 plus 0.5 rainfall in inches. And it's the same story again. So this was saying every inch gives me 500 kilograms. This is saying, well, every inch will give you half a ton. Half a ton is 500 kilograms, so they are the same. So when you think of the y variable, just divide both sides by the same thing. What happens if you have both? So if I take the old equation, I want to change the inch into millimeters, and I want to change the kilogram into tons. Well, what do I need to do? You can do the scaling one at a time. So first divide both sides by 1000 and then do the scaling of the rainfall variable here into millimeters. So if you do that, what you are going to get is what you see here. Let me remove the cluttering here. So what you are going to get is that one. So it's the same story. A millimeter of rainfall is going to give you 0.002 tons, which is same as 2 kilograms, which is same story. Let's move on to an example where something was estimated in R. And of course, in one case, we had Y regressed on X simply, and then Y regressed on x over 10. I am just using the indicator operator here to show you what you do in R to do it on the fly, but that's not important. And in the third one, we had y over 10, okay, scaled down by 10, regressed on x. So there are three equations, 1, 2, 3 in here, and that's what we have. So without scaling, we had this. The slope was 0.385 and the intercept was 1.418, roughly 1.42. What happens when you, instead of using x, you use this one? Well, your slope term becomes a new slope term that's scaled up by 10. Okay, so instead of having 0.385, you have 3.849. Well, that's 3.85, 10 times bigger. So that's what the scaling of the x variable does. Now, if you think of scaling the y variable, that's what you have in the last column here. So if I scale my y variable by a tenth, that's the equation, then this is what I get. What is that? Well, my slope is divided by 10, that's here, and my intercept is divided by 10. So the same story again, but that's what happens. Scaling is not going to change the story. If that is the truth, then why do we need to scale? Well, we can have different reasons why we scale. We can scale because we like our natural units. So if I grew up in a country that is kilograms instead of pounds, I am going to prefer kilograms or metric units in general than British units. But if you grew up in a country that is British units, it doesn't mean just Britain. It could be Canada, for example, for weight and so on. Then you are going to prefer pounds rather than kilograms and so on. So people have natural units, and when they write, they use different things. But then if they give you data that are in units that you are not used to, you will need to translate those units into your own, which is like going from inch to millimeter or the other way. That's one good reason. But what other good reasons are there? Well, even if I stay with metric units, I might prefer to use tons if I am more comfortable expressing yield in tons rather than kilograms, or it could be the other way. But it's customary to express yield in tons in many places, so that is another reason to scale. So it makes it easier for you to write and to present things. You might prefer to say, well, you get an extra so many tons if you do this and so on instead of kilograms or grams. That's a good reason. Of course, if you are talking about soil nutrients or soil quality and so on, like organic matter and so on, it might be a different set of units that you prefer, and that means again you might be translating scaling things. That's a second reason. Another one is, well, to avoid haphazard scales. So some you have a model, some coefficients are massive, some coefficients are very small, and that doesn't look good in a table. Why doesn't it look good? Well, because if I have a story, I have a model, and then I have an intercept, and then I have a coefficient for x1, x2, and this is 578, this is 0.02, and this is 20,000. This doesn't look good, different scales. Okay, so if this is for something that's measuring income as a function of different things, and income is measured in dollars, well, why can't I measure income in thousands of dollars? So that would make this smaller, that would make that smaller. This will be even smaller, so what I have to do is scale this again to bring them to a comparable scale. So I'm giving you maybe something that's made up, but I can tell you, you can run into that. So if people give you data, or whether it's a Department of Education or the Department of Agriculture or somebody else, it might come in such haphazard units, or if you collect it yourself, that it doesn't look good if you just stick to the raw data. So you need to change that. So 3 reasons I have given you. The last one I am going to give you is something that has to do with computation. Whether a researcher is estimating a regression, which means they are using the normal equations, you remember them from previous lectures, and doing the calculations on a scientific calculator to come up with estimates, which is what people used to do, or if you are using computer software. In both cases, you might be happier if you scale your units. So I would not do a regression where income is in just dollar units. That would be massive numbers. Like I would have somebody's income could be 75,000. I would never want to have this in my normal equations where the coefficient or the slope term is involving things like this. Okay, that's massive numbers. I don't want to calculate those numbers. These are huge. Okay, I want to scale them. So if I'm doing manually, I wouldn't want to do that. I would scale. How about if I'm using software? Isn't current software very powerful now? You know, you can give it anything and it gives you results just in a breeze. Well, no. If you have complex models, I have master's, PhD students, sometimes their models fail. And the first thing I tell them is, have you scaled your variables? Why don't you just scale them? Now, I have been telling you about scaling things using simple things where you go, your y variable gets divided by 1,000, okay, or your x variable gets multiplied by 254, or by 10, or by 100, and so on. Well, you can scale by anything. I can divide this value by its mean value, so the new mean becomes 1. But don't worry about this if you don't understand. But that's what real research might involve. You scale the variable by its mean, so 1 is equivalent to the sample mean. Okay, actually translation is the next thing. So translation means redefining the 0. So I just showed you an example going from x to z variable. The x has a mu as a 0 as a center, but z has 0 as a center. So you are shifting the 0. If you go to the definition, translation means adding or subtracting a constant from a variable. So that's what I'm doing. If it's measured on the x-axis and it has a 0 here, and then I add or subtract some constant, some translation constant, and then the 0 becomes something else. There is a very simple example which many people might recognize. If you go from degree centigrade to degree Kelvin, degree Kelvin starts its 0 at what would be equivalent to minus 273.15 degrees. So they are very different measurements. The 0 for degree centigrade is here, and the 0 for degree Kelvin is actually minus 273.15 degrees centigrade. Simple example. This doesn't involve scaling because a tick in degree centigrade or 1 unit change in degree centigrade is the same thing as a 1 degree change in degree Kelvin. So the scales are the same. If temperature goes up by 10 degrees Celsius, then it's going to go up by 10 degree Kelvin. It's the same measure unit in terms of scale, but it's a different unit in terms of where it starts, and that's called translation. If I had something written in terms of a relationship between biomass, and that depends on temperature because you need enough heat units to generate so much biomass, okay, it's easier for plants to grow when daylight is longer and so on, and the temperatures are higher. So let's say for whatever reason, we have a model. Well, if you want to translate this into a model where temperature is measured in degree Kelvin, then what you will get is this one. Why is that? Well, degree Celsius or centigrade is equal to what? From the Kelvin, you have to subtract 273.15. And if I put that number right here, I am going to get this. What has that done to the regression? Well, the slope doesn't change because there is no scaling. A unit change in temperature, whether it's measured in degrees Celsius or degree Kelvin, has to mean the same thing in terms of biomass change. What changes is the intercept. So if I put a 0 here for degrees Celsius, it means 273.15 here. Well, then I have to get the same biomass. And the only way I can do that is if this intercept is changed. So 273.15 times 3.6 added to 10 has to give me that number. And that's how it works. Try it. Well, if we stay with temperature, we have even a more interesting case where we have both scaling and translation, because when you go from degree Fahrenheit to degree centigrade or from degree centigrade to Fahrenheit, you have to scale and translate both. So if I had degree Celsius, well, I have to scale up by 9/5, which many people would remember from their science studies, and then add 32. So scale, translate. So we'd have something like that. So here there is 32 steps, and here there's about 17.8. Just check this. And both the scale and the zeros are different places. So that's what we have here. And if I want a relationship that's equivalent to this in degree Fahrenheit, then it's going to be that one. How do I get that? Well, what you need to do is substitute for degree Celsius here in terms of how you would write it. So degree Celsius, okay, if you think of what it means in terms of Fahrenheit, is F minus 32 divided times 5/9. So if I put this in here, it's going to give me this. So because we are doing scaling, our slope goes down to 2. Why is that? Because a tick or a unit change in degree centigrade is equivalent to 1.8 times a unit change in degree Fahrenheit. So that's why this is going down. And of course, because we are translating, we have a different intercept. So this is easy to see. All you have to do is just plug in, instead of having degree centigrade, you substitute for that one in here. And if you do that, it means you have that times 5/9. And this is going to give you something that is 54 plus 2 times degree Fahrenheit. And you can check. So if you check when C is 0, F is 32, the biomass has to be same from both equations. What you are going to get is, of course, 10. It doesn't matter whether you use this equation or the original one. And it should be same when you have a different temperature. Biomass from both equations is going to be 100. So again, whether you translate and scale, the regression story or the model is going to stay the same.